Thanks, Mihai. And yeah, thanks to all the organizers for inviting me to come talk. It's great to be part of this conference. This paper is joint work with Michael Wong, who's a PhD student at MIT, and Alan Zhang, who's a PhD student at Harvard. I think they're both here so they can field any difficult questions that come up. The motivation, I think, for us for this paper starts from a paradox that we see looking out at the media landscape these days, which is the cost of producing and disseminating and consuming information has fallen dramatically in recent decades. A naive, simple model of the world would suggest when that happens, we should see increasing convergence of people's beliefs, the information sources available should become better and more trustworthy, and the accuracy of everybody's beliefs should increase. Obviously, that doesn't sound a lot like what has happened. According to lots of different measures, what we've seen instead is trust in media falling, not rising, and also fragmenting along ideological lines, and beliefs about facts diverging rather than converging. And so lots of people, of course, have thought about what might be wrong with that simple account and explain this paradox. And I think if you look across those different accounts, probably the leading one is that this is a result of different forms of psychological bias in the way people process information. That could be motivated reasoning, confirmatory bias. We're very much, I think, on board with that view, and indeed bias will figure in our model. But we want to note that in the simple versions of those models, I think in order to explain the facts we see, the magnitude of those biases needs to be very, very large. And so if we think of it in terms of people's implicit motivations, the weight that they put on psychological utility for confirmation or whatever else would need to be really large relative to their preference for accuracy. Second possibility is that these kinds of things could be exacerbated by selective exposure. People are not seeing all the information sources, they're only seeing selected ones. That also certainly could play a role. But the challenge there, I think, is that empirical evidence so far suggests the magnitude of that selective exposure is actually relatively small and a lot smaller than many people assume. Finally, we're going to build here on some earlier work in Bayesian models of trust and reputation in media markets. Limitations of those, of the kind of fully Bayesian models in that space, is that it's not possible for the usual reasons to get in the limit over time as the amount of information gets large to have polarization of beliefs or divergence in trust. You can get that in the short run in those models, but eventually everything has to converge. So our goal here is to say, can we think about a unified explanation for these different patterns that we're seeing that would hold even when selective exposure is limited, consistent with the empirical evidence, and also where the psychological biases at play might be relatively small, and where fundamentally the agents in the model put a lot of weight on learning the truth, care a lot about learning the truth, but might be subject to small psychological biases. And the basic idea that we're going to explore is that those small biases may interact with endogenous trust. That in a model where agents are simultaneously trying to learn facts about the world and also trying to learn which sources they can trust to tell them about those facts, that the endogenous trust process can blow up and amplify the impact of even small psychological biases. So the form of the model is going to be the following. We're going to think about a sequence of periods. In each period, there's an independent IID state, omega t. Everything in this model is going to be standard normal. So omega t is standard normal IID. And so we're going to think of those states as like different issues that we're trying to learn about each period. So maybe in one period, we're trying to learn about global warming. In the next period, we're trying to learn about what happened in Afghanistan. In the next period, we're trying to learn about testing for the coronavirus and so on. Agents in the model are going to have access to two kinds of information about omega t. There are a bunch of information sources. Those produce signals, SJT, that are informative about omega. But they're potentially very informative. So we're going to be focused on cases where actually the amount of information a Bayesian agent, perfectly Bayesian agent, could extract from those signals is large. But The problem is that their accuracy and biases are uncertain, and so the agent needs to learn that as well. The other key element in the model is feedback, which will denote XT, that agents gather by direct observation. So if we're trying to learn about global warming, this might be what the weather looks like outside the window. And the key difference between XT and SJT is just, I don't need to learn about the accuracy and bias of XT. I start out believing that it's unbiased and relatively confident in its accuracy. So we're going to have in mind that XT is noisy, but I know I can trust it. SJT is potentially a lot more informative, but I don't know whether I can trust it. And that's what I have to learn. So we're going to be focused on the limit as t goes to infinity of this model. And over time, the agents are going to be able to learn about the properties of SJT by comparing what the information sources say to their own observations over time. And the basic results, which we'll obviously get into in more detail, are we show that even arbitrarily small biases in XT can lead to large polarization of trust and also large polarization and divergence in beliefs about omega t. And that this can be true whether or not there's selective exposure. So it can be true in a case where agents just observe like-minded sources, but it can also be true in a world where everybody observes all of the sources. This model builds on a lot of prior work, and I'm not going to take time here to go through it. One particular connection that I just want to flag, there's obviously a long literature on asymptotic learning. And what we're going to be doing here is particularly related to some work by Mohamed Yildiz and Doron Asimoglu and Victor Chernozhukov, Rajiv Sethi, and others, thinking in kind of more abstract settings about settings where agents are trying to both learn about states and learn about the properties of signals. And there's, I think, a pretty deep, strong connection between what we're showing here and some of their results about how the simple predictions of Bayesian models can change in that case. Okay, so here's the model. As I said, we have these states each period that are normally distributed IID. We want to introduce a political dimension to the model. And so the way we're going to do that is to also have an ideological state, what we'll call the ideological valence of the issue in each period, RT, which is also standard normal. And so the way to think about RT is that's the position on this issue that is most favorable to conservatives. And then minus RT is the position that is most favorable to liberals. And we're normalizing everything, so 0 is kind of the politically neutral position. So both of those vary over time, omega and R. We're going to assume that R takes the form below. And what that does is allows for the possibility that the ideological state is correlated with the true state. That's what we're ultimately going to think of as what we'll call ideology. So that would, if R is correlated with omega, that would mean the conservative position is in fact closer to the truth on average, or farther from the truth on average. The Republicans are actually right, or the Republicans are actually wrong on average. We're going to allow for that, but we're going to be interested in the case, we're going to focus on the case where, in fact, the true value of this gamma correlation is 0. So agents may come to believe that it's non-zero, but we're going to focus on the case where it's actually 0. And then R tilde is the residual variation in R. So R tilde is the component of the ideological state orthogonal to the true state. Signals, also standard normal. They are correlated with omega. That's the whole point. The correlation with omega is alpha j for the jth signal. They may also be correlated with the ideological state. That correlation is beta j, with the residual part of the ideological state. And then there's some remaining IID error in the signals. And so we're going to think about alpha j, the correlation with omega, as a source's accuracy. Trust in this model is agents' beliefs about alpha j. And we're going to think of beta as the bias of the source, to what extent its reports systematically correlated with the political state. Feedback, XT, takes exactly the same form. Just use different labels for the parameters. So A here is the accuracy of the agent's feedback. B is the agent's bias. And then, as I said, the key thing that distinguishes XT is that the agent believes it to be unbiased. And so the agent is going to have a dogmatic prior, as I'll say in a sec, that B naught, the true value of B is equal to 0. And then when we introduce bias to the model, that will be allowing actually the true value of B might not be 0. So I'm mostly going to talk today about a baseline model in which there's one agent. That agent observes exactly one SJT in each period. And we're not going to model the demand process for those sources explicitly, but we're going to assume that in the limit, each source is observed infinitely many times. So agents may eventually converge to almost entirely looking at sources that are aligned with them or that they prefer, but there's enough experimentation that they see all of the sources ultimately infinitely many times. And we're also going to basically assume that XT and RT are observed. We'll in fact assume that they are observed in some periods and not others with independent probability. And that just captures the idea there may be some periods where the agent knows something about the issue at stake and has some direct observation about it, knows what the political positions are, and then other issues come along where the agent doesn't know anything. So this is what we call like the single homing model, the one where the agent observes just one source. Later, I'll come back and talk about the extension of this to multi-homing, where the agent might observe many sources. That's where we get into these selective exposure questions. And then if there's time, briefly talk about, we have at the end of the paper a model of endogenous media entry where the positions of these sources is endogenized. And then we can think there about what happens with monopoly versus competition and how does changing mix of sources in the market affect the outcomes. Okay. So that's the basic setup. Here's some examples to kind of make this concrete. So,
did you say that XT is less accurate than the signal SJT?
Yeah, so far I haven't said that. These parameters, the range of these parameters covers 0 to 1, and so it is possible that X is more accurate. But as I'm going to say in a sec, we're going to focus on the case where A is small. So we're going to be, that's not an assumption, but the case of interest in the propositions I'll show you is the one where A is small. So what I know, if I want to learn about global warming, looking at the weather in Palo Alto is not a great way to do that. The agents realize that looking at the weather in Palo Alto is not a great way to do that. Okay. So if that's the issue, global warming, we could think, for example, of omega t as the expected rise in temperature if we do nothing. In that case, the ideological state would be negative. That is, conservatives, the position that benefits conservatives on that issue or that they're supporting is that number is low. Liberals are arguing that it's high. Signals might be media reports on climate science, and XT might be, as we said, what I see out my window. Could imagine another day where the issue is the coronavirus. Maybe omega t is what is the actual social return to being fast in reopening schools and businesses. RT would be positive. Conservatives are on the side of that number being high. Liberals are on the side of it being low. S might be media reports of experts and public health officials and models. And XT might be something like, what cases of the coronavirus do I observe in my social network? And what's going on in my local community. And so here, to produce question, we're going to be mostly interested in the case where the SJT may be highly informative, but their accuracy is uncertain, and XT is noisy, but as we said, has known properties.
Matt, if I can just interrupt for a second, there's at least one question in the Q&A, so let me just encourage your co-authors, if they want to reply on the text chat or at some point bring it to your attention.
Excellent, excellent. Okay, so formally what we assume about prior beliefs is essentially the agent has a full support prior on the parameters of this problem subject to the restriction that they believe XT is unbiased. So to say that a little more slowly, the persistent states in this model, the persistent parameters that the agent is trying to learn are theta, which is A and B, the parameters of XT, alpha and beta, which are vectors. Those are the parameters governing the information sources, and gamma, which is this ideology parameter. So that's what the agent is trying to learn. We assume, our kind of key assumption is that the agent has a full support continuous prior on all possible values of theta, subject to the restriction that the value of b is equal to 0. And so the agent has a dogmatic prior, believes with probability 1 that their own xt is unbiased. We are also, and there's some technical detail here, which I'm going to not go into in detail, but which you can refer to the paper for. We're also going to be focused on the case, we want to focus on the case where the agent has a strong, accurate prior about the value of A, the accuracy of their own signal. But we want to retain the property that that has full support, so that if the data sufficiently strongly contradict that, the agent's belief about A might change. So we're going to think about a limit of priors that become increasingly concentrated at the true value of A naught with full support. And our main characterizations are going to focus on the limit of the equilibria as those priors become concentrated. And what that's effectively going to do is it's going to mean that if A naught is consistent with the data that the agent observes, the agent will believe that that's the true value of A. If not, the agent will end up believing in the value of A closest to A naught that is consistent with the observed data. Okay. So a couple of points to just step back and discuss here. So the idea of this feedback is obviously really essential in the model and is going to be the only way that an agent in this model can ever learn which sources they can trust. So as we've already said, the key properties of xt, of that feedback, are one, the agent believes it is unbiased, and that the agent has this strong prior on its accuracy concentrated at the truth. I've been talking about this in terms of feedback that agents observe directly. So, following this debate, I can then look out the window and see what the weather is. There are other interpretations, I think, that also are consistent with the model. One is that it's direct observation, but it's prior rather than ex post feedback. There's no difference there formally. You could also think, instead of observation, that this is something like reasoning from first principles. So there's some reports about what the top marginal tax rate should be, and I am going to think about that and maybe write down a model. That could be a version of xt if I believe that my own reasoning is unbiased. And it's also possible that there's some source that the agent axiomatically decides is unbiased a priori, and that would also be consistent with our model of xt. The key then is going to be that the agent might be wrong, and there actually is some bias in what they observe. Our leading interpretation of that is that the agent either underweights or ignores or forgets or distorts feedback that goes against her initial or preferred ideology. And so I won't go into the details, but there's obviously a rich literature in psychology and economics on possible forms and micro foundations for that kind of bias. And I think basically you could plug in any of those underlying micro foundations and it would be broadly consistent with what we have in mind for xt. Okay. So what I'm going to do now is first characterize asymptotic learning in the model, show you the formal results on how beliefs converge. And then I'm going to talk about the properties of that limit and sort of spend some time going through what do those limiting beliefs imply for trust, what do they imply for the agent's confidence, what do they imply for polarization, and so on. Okay. So let's now think about this learning problem that the agent faces over time. Remember that what the agent ultimately observes each period is xt, rt in the periods where those are observed, and one particular s, jt. Remember that every variable in the model is standard normal, and we're assuming that's common knowledge. The agents know that. So the only uncertain moments of the data are the correlations of these different variables. So you can think about sufficient statistics for the agent's learning problem are the correlations rho xs, the correlation between x and the elements of x, that's a vector. Rho xr, the correlation of x with r, that's a scalar. And rho rs, the correlation of r with s, and that's a vector. So that information exhausts what I could learn from the data about theta. If I knew the true values of those correlations, there would be nothing else to learn from the data. And so we're gonna think then about the set of parameters that those correlations identify. So we'll call the identified set, which will denote I of R, the values of theta consistent with correlations R. And then we're going to be particularly interested in the subset of that identified set that is consistent with the agent's belief that B equals 0. So I of R given B equals 0 is the subset consistent with B equals 0. And just to kind of sketch ahead of time how learning is going to work here, it should be pretty obvious, given the way we've set this up, the agent will be able to learn the true values of R perfectly as t goes to infinity, because the agent has infinitely many observations on all of these different pairs of variables. And so the agent learns the correlations perfectly. There's nothing else the agent can learn. And so the agent's beliefs about theta are going to converge to this identified set that is consistent with B equals 0. So we show that formally in the paper. If the true correlations are not, then in the limit, the agent's posterior distribution converges to a limiting distribution with support on that identified set. And because there's no other information in the data within that set, the agent's limiting posterior is just proportional to her prior beliefs. There's no additional information learned within the identified set. Now, we want to think then, well, what does that identified set look like? Because that's going to define what agents come to believe. And this is the one point in the talk where it's worth kind of, having a drink of coffee and paying attention to the algebra, because the way the parameters relate to these correlations is going to be really important for the results I show you later. So let's think about what those correlations are in reality. So what is the correlation between X and S? It's going to be given by this expression, A alpha plus B beta. What is that doing? Well, A alpha is the correlation induced by both X and S's correlation with omega, and B beta is the correlation induced by both X and S's correlation with R. And so my feedback is going to be more correlated with an information source if they're both accurate, and also if they have the same bias. B and beta have the same sign, and they load on R in a similar way. You don't need to worry as much about the XR and RS terms for now, but they have similar form. There's a term because of the correlation with omega and a term because of the correlation of R. So if we think about this from the agent's perspective, if we believe that B equals 0 and we know that, then we have the following inference. So the agent will, any theta that is in that identified set for the agent will have the property that alpha is just the correlation between X and S divided by A. Gamma is the correlation between X and R divided by A, and so on. And I want you to just dwell for a second on that expression for alpha, because this is an important intuition in this model is my trust alpha in an information source is ultimately going to be determined by how correlated that information source's reports are with the feedback I observe. And how sensitive my trust is to that correlation is going to depend on A. And if A is small, as we've said is the case we're interested in, then even pretty small differences in that correlation translate into big differences in my trust. Because if my own information is noisy, it's never very correlated with anything. So even small differences in the correlation matter a lot for my inferences. That's where we're going to get amplification in this model. Okay. Now, a final detail that's important to see is the identified set for the agent with B equals 0 places bounds on the possible values of A. If you go back to that expression for rho XS, it is not, if I believe B equals 0 and rho XS is positive, I can't believe that A equals 0. A has to take some high enough value to be consistent with rho XS. In particular, A needs to be at least as big as rho XS since alpha is less than 1. So there's this lower bound on A, and that is going to be, for example, it must be bigger than any of those observed correlations. And the exact condition is that A has to be bigger than this expression, which is instead of the correlations, It depends on the square root of zeta j, which is the r squared from a regression of x on both r and s. So because I observe r and s simultaneously, the information bound on x is going to be determined by the joint covariance of those different variables. So there's this lower bound on A. So here's just restating what we just said. The identified set consistent with the observed data is non-empty and consists of all theta with A above that bound, B equals 0, and then alpha, gamma, and beta satisfying these conditions. And note that there's a one-to-one correspondence here between values of A and elements of that identified set. There's one element for each value of A. So if I pick out a particular value of A, then there's a unique value of theta that the agent comes to believe in. And that's where this concentrated prior assumption fits in. We're going to focus on the limit of a sequence of priors that become concentrated at the true value of A naught. And as we show formally in the paper, that is going to effectively pick out the element of this set that is equal to A naught if that's in the set. And if not, it's going to pick out this lower bound that is consistent. So whichever of those is consistent with the data. So this just states that that limiting posterior as A naught has a concentrated prior is just what I showed you in the previous proposition, except now it's a unique value with A star equal to that max, the other parameters equal to the associated values. Okay, and this ultimately, this theta star is what we're going to focus on characterizing. So let me talk a little bit about that characterization. So for simplicity, let's think about a case where the agent's own bias is weakly positive. So it's a conservative agent. We'll assume that at least there's some source in the market that has non-zero alpha, so has some information. And then as we've alluded to, we'll be particularly interested in cases where the bias is small. A naught is also small. And the potential information of the sources is large. And we're going to capture that by assuming that at least some of them are on or close to this frontier where the alpha and beta take the maximum possible values. Alpha squared plus beta squared equals 1. Okay, so here then are some characterization results. So the first thing we want to think about is what we call the agent's confidence, which is just the agent's belief about A, the agent's belief about the accuracy of her own feedback xt, i.e. how good do I think my reasoning about taxes is, or how good do I think my ability to infer about global warming is from my own observations. So when is the agent overconfident? So the agent has correct confidence equal to A naught if A naught is consistent with the observed data. When is that not true? It's not true when this bound is above A naught. And remember that bound depends on the R squared from a regression of X on R and S. So intuitively, when is that going to be the case? When is the agent's belief about A going to be greater than A naught? Well, first observe that R squared, if we omitted S and just thought about the relationship between X and R, is equal to B naught squared, the agent's bias squared, because that's the correlation of X and R in the baseline case when gamma naught equals 0. So the right-hand side of that expression has to be at least B naught. And so the agent will tend to be overconfident whenever A is sufficiently small relative to B. And so that's going to, in general, the agent will tend to be overconfident in potentially in this case that we focused on where A is small. Second, note that this, if the source SJT we're talking about is on the frontier, then the R squared is going to be A squared plus B squared, because now I observe R, and then I observe something which is just a sum of R and omega, some weighted average of R and omega. So between R and a linear combination of R and omega, I can perfectly predict R and omega, basically, and that leads to this R squared. And so in that case, the agent is always overconfident. So we state this as a corollary of the main learning theorem. For any bias, no matter how small, the agent will be overconfident in these cases. When A is sufficiently small, And the bound that it has to get below is not that small in a sense that it's greater than B naught. So even when bias is small, A needs to be small relative to B, but not too small. Also, the agent will always be overconfident if at least one source is on the frontier, or we show in the paper sufficiently close to the frontier in an appropriate sense. Next, I want to talk about trust, which is, I guess, in some sense, kind of the thing that we start out being most interested in here. So trust in this model is the agent's asymptotic belief about alpha, about the accuracy of the information sources. I pointed out to you before that the agent is going to infer that alpha equals rho, the correlation that she observes between her feedback and source J, and A star, her belief about the accuracy of X. Right? So we had that expression from before. If we plug in what the true value of that correlation is going to be, A alpha plus B beta, we get this expression for trust. And so I want you to observe a few things about trust asymptotically. First, we see confirmatory property of trust in the sense that agents are going to trust like-minded sources more. So for a given value of A and alpha and A star, if B and beta have the same sign and are bigger, the agent will trust them more. I trust sources whose bias has the same sign as mine and is large. Second, notice that trust interacts with confidence here. So as I get more overconfident, I become less trusting in everything. And that's going to be a mechanism in the model whereby agents may become, end up underweighting the accuracy of even perfectly accurate sources. And finally, we see this amplification mechanism when A is small, even very small biases and small slants on the part of the information sources can translate into large differences in trust. So you can see this graphically. I think a nice way to represent trust in this model is to think about the space of possible sources alpha and beta. That's given by this gray area. That is, think of that like a production possibility frontier of the possible alpha beta combinations that satisfy alpha squared plus beta squared less than or equal to 1. So those are the possible information sources in the model. And then these blue lines are analogous to indifference curves. These are isotrust curves along which the agent's trust is constant. So you can see agents trust sources more as we move to the northeast. The slope of those lines depends on the agent's bias relative to the accuracy of her own feedback. And so you can see that as B gets bigger, those lines tilt to the right, and the agent's trust shifts toward more biased sources and away from more accurate sources. And the point at which those are tangent is what we'll call the agent's trust maximizing source, the source that yields the highest possible trust. So our corollary summarizing this, for any bias, no matter how small, suppose at least one source is located on the frontier, or again, this would be true if it's sufficiently close to the frontier, then the agent will trust unbiased sources too little. That's because she's going to end up being overconfident. Provided that A is small, she will trust sufficiently biased like-minded sources too much, and she'll believe that opposite-minded sources, sources that have bias opposite to hers, are actually perverse in the sense that not only are they inaccurate, but they have negative correlation with the truth. So I come to believe Fox News is not just a noisy source, but a perverse source that's like actively trying to convince people of the wrong thing. And finally, regardless, no matter what A naught is, I'm going to believe something close to my trust maximizing source is perfectly accurate, even though it might be very, very noisy. Last characterization I want to spend some time on is polarization. So this is what happens to the agent's beliefs about omega then in the limit of this model. So to do that, we're going to say, now suppose that the agent's beliefs about theta are that limiting posterior. Then as periods come along, and in each period she sees some signals and tries to learn about omega, what do her beliefs look like? And for this, for simplicity, we're going to focus on the periods where she doesn't see X and R. So we're just focusing on beliefs based on the signals she observes. Then proposition, her posteriors on omega, each period having observed S, by the usual results, will just be normal with mean equal to S times her trust alpha star and variance 1 minus alpha star squared. we're then to think about polarization, we're going to think about one agent that's biased to the right, one agent that's biased to the left, and ask, and for simplicity, imagine they have the same A's and they have opposite and equal biases, and ask how much are those agents' beliefs about omega going to diverge. And to have a summary statistic, we're going to define expected disagreement to be the expected squared difference scaled so it lies on 0, 1. So you can imagine in this model now where the agents are going to end up diverging in their trust in these sources, potentially to a large degree. Remember, my trust maximizing source I think is perfectly accurate, and your trust maximizing source you think is perfectly accurate, and those are very different. That can produce large divergence in beliefs about omega. So we show if we're both looking at the same source and it's unbiased, disagreement will be 0. If we're both looking at like-minded sources, disagreement will be positive. And if those are our trust maximizing sources, disagreement polarization will be large. And as A gets small, it'll become arbitrarily large. So as A gets very small, we end up disagreeing maximally. Every period, I think omega is as big as it could be, and you think it's as small as it could be.
Sorry to interrupt. You have 10 minutes left.
Yep.
It would be great if you can leave about 5 minutes for discussion.
Great. Yeah, I was going to wrap up in 3 minutes. So let me just summarize the remaining results quickly and then leave some time to talk. So we have some other characterization results about ideology. What does the agent come to believe about gamma? And so as you can probably see, an agent in this model is going to come to believe that, in fact, the true state is correlated with R in the direction of their bias. So agents with right bias endogenously come to believe that the Republicans are actually right about the world, and agents with negative bias, even arbitrarily small bias, come to believe that the Democrats are right about the world. Characterize the perceived bias. What do the agents come to believe about the biases of the sources, and also their error? To what extent are they actually making accurate or inaccurate inferences about omega? Okay. So the last 2 parts of the paper, which I'll just kind of give an overview of here so we leave some time to talk. First, we extend this to the case of multihoming. So we think about, instead of the agents observing one source each period, now the agent observes all of the sources in the market every period. And we're interested in that because there's an intuition that that might help. But part of the problem here is agents are only observing their own sources. And if everybody could see everything, if the Republicans read the New York Times and the Democrats read Fox News, everything would get better. And so we want to evaluate that claim. We can think about what the specific mechanisms might be. We show that in some sense, those mechanisms do exist in our model. Those are correct intuitions. But nevertheless, in this model, multihoming does not help in general, and actually can make divergent trust and polarization worse. And so I won't go through the details of that. You can see it in the paper. I think the high-level intuition is that think about this case where I have this trust maximizing source that I believe is perfectly accurate. Now, when I observe all of the sources in the market, it's going to end up not changing that inference. I will just believe that the other sources in the market have correlated errors such that I end up just putting weight on that same source anyway. That's one way to think about the intuition. So that's summarized in the paper. Finally, we have a simple model of media entry to think about where sources would locate endogenously in this market. And that basically just delivers a monopolist will choose an unbiased position in a market where there's kind of equal types, biased right and biased left. There will tend to be very little polarization. If we start adding partisan sources to the market, they're going to endogenously locate at these trust maximizing points on the frontier, and that produces large divergence and large bias due to the entry of partisan media. Okay, so this is just summarizing those results. You can see those in the paper. So to conclude, we have this kind of paradox that we've seen in recent years. We are very much on board with the idea that psychological bias plays a role in that. However, in the standard account, you really need people to care very little about learning the truth relative to these biases. And so I think the kind of key takeaway from this paper is the agents in our model actually care a lot about learning the truth. In fact, they care only about learning the truth. they believe that they are acting rationally. They believe that they are doing a really good job of interpreting the information available and trying to learn the truth. The problem is because of these very small biases, they end up diverging from that pretty dramatically and having polarized beliefs. So I'll stop there and welcome any questions. James.
Hi, so I was wondering, I just want to make sure I've got this correct. If everybody were to report their track record, their evaluations of these statistics, and they were to be aggregated and everybody could observe those at a relatively low cost, in this setting, everything would be fine. Is that correct? That conditional on people honestly report, you know, which is a big thing. But,
yeah. So I guess we don't have a formal answer to that in the paper, because in the baseline model in the paper, strictly speaking, there's a single agent, and so we don't write down formally in the paper what one agent believes about other agents in the market. If you did write down that model, I think the one way you could write it down is, I believe that I am unbiased and my XT is unbiased, but I entertain the possibility that everybody else may be very biased in their beliefs. And we actually have an extension at the end of the paper along those lines. And in that kind of model, that does not help. Being able to observe what other people think does not help. And I just come to believe the Republicans are crazy, basically. If you add the other case where I have a dogmatic prior that I and everybody else is unbiased, then it's hard to say what happens, because the data are going to violate the agent's model of the world. Like, then there's just no parameters that the agent can square with what they observe. And so the whole learning process gets much more complicated in that case.
I see. Thanks.
Matt, this is more of a clarification. So I guess in your model, the agent is misspecified, right? But nevertheless, the agent is always able to rationalize sort of infinite data with her model of the world. Is that correct?
Yeah, that exactly. And that's really important here. So, you know, why does that happen? It happens because the full model is unidentified. So this identified set, remember, if we go back, you know, the full identified set of, given what I observe, which are these correlations, there are infinitely many parameters that might rationalize those correlations. And I can never reject that B equals 0. So there's always an element of that set consistent with B equals 0. So that means that the biased agent is never, what the data that they observe in the world is never inconsistent with their model of the world, is never inconsistent with B equals 0. That just affects which parameter values they then focus on. If that makes sense. And so you end up converging to this part of the space, which is different than the true parameter values.
Thanks.
So if there are no more questions, I know that Michael, your co-author, has been answering questions in the Q&A text box. So I don't know if Michael wants to share anything with us about those questions and his answers.
Sure. There was a question about, how does relaxing the assumption of B equals 0 affect the results? And there were also some questions about whether people identifying themselves as liberal or conservative is consistent with the model. So I'll answer the second question first. So So our model sort of allows agents to learn whether the true states are correlated with ideological valence. So, you know, a left biased agent would learn, in fact, that the true state is correlated sort of negatively with the, or correlated with like negatively with the ideological valence. So this is sort of consistent with the idea that people end up identifying themselves as liberal or conservative. To the question that, you know, what happens if, you know, there's no information source where the agent believes is unbiased. In that case, the agent's problem is fundamentally unidentified. So she would not be able to reject either, you know, all sources are unbiased or all sources have accuracy 0. And at least one of them is maximally biased. So that sort of suggests that, you know, when there's a lot of sources that are whose accuracies are unknown, you know, having some sort of assumption where something is unbiased is actually helpful in identifying which sources are useful. And Matt, maybe there's one more question on the Q&A, which just asks, is there any normative analysis derived from the results? In particular, like if small biases are amplified by endogenous trust, what can we do about it?
Yeah, that's a great question, and we unfortunately don't have policy recommendations here. I think that like the first thing is that this model argues that some of what we are currently doing, which is kind of blaming everybody for not caring. We often describe people as surely they don't care about the truth. Surely they just want to have their beliefs confirmed. Surely they're not well-meaning and interested in learning the truth like we are, is counterproductive and unlikely to help if this was the true model of the world. And then, you know, how do we improve things here? I mean, partly you know, one interesting idea is related to James's question, because in a model, if you extend the model to have communication among different agents, then it's interesting to think about under what models that might help. You know, there's literature on how do you debias people and how do you help people recognize the biases in their Bs. So if the biases in X, so if you could get people to recognize those biases, that would help here. But I think it's a great question, and I guess it's not an optimistic paper. We think of it as an optimistic paper because it's like, actually, maybe everybody is trying to learn the truth, but it's not an optimistic paper in providing a simple solution. Let me just say one other thing about the question about people's ideology, and is it consistent for people to be liberal conservative? I mean, that's actually something we've wrestled with a lot, and it's subtle here, and it does reflect a limitation of this model. So, you know, I alluded to this bias might be related to your initial ideology. And so if we think of ideology as this parameter gamma, that would be like you have a full support prior on gamma, but it might be quite concentrated in the conservative side of the spectrum. And then that might lead you to have these biases in a conservative direction. Something it's really important to flag that we're not doing, which in, for example, Matt Rabin's model of confirmatory bias, they do, is in that case, you might want to have your bias B be endogenous to your evolving beliefs about gamma. And so if my bias was a function of my belief about gamma, my ideology, then you might think as my ideology moves through time, my bias moves through time. And that's something we're not doing. We're just fixing the bias. That might be a function of, you know, what environment you grew up in as a child, or what your parents' ideology was, or whatever. And then your ideology can move around over time. It'll end up being consistent with your bias, but it can move, but we're not endogenizing that relationship dynamically. James.
I'd just like you to speculate on something for me. So it seems to me that a lot of work in getting this large amount of polarization is coming off the fact that the agents have a misidentified model with their bias. And so when we give them infinite data sets, then that ends up really determining that they have to skew their estimates of theta a lot in order to make it compatible with this tiny grit of irrationality. So could it be the case that by limiting the amount of data that people actually get in order to make their decisions, that we end up improving the accuracy of people's beliefs about the state of the world by preventing them from getting these really polarized views of the bias in the media sources.
Yeah, I think that's a really good question. And I think that's an accurate description of what we're doing here and some of the prior work, like the Asimoglu, Chernozhukov, and Yildiz paper that I mentioned. So that is definitely what is happening here. Does less information help? I'm not so sure. Formally in the model, it's just going to depend entirely on what the priors are. And so if people start out with, they have full support priors, but those priors are concentrated around the right values, then giving them little data is great. If they're concentrated on really wrong values, giving them little data doesn't help at all. And it's also related to the point that Michael was just making, that, and also to the answer to Naveen's question, the fundamental unidentification of the model is really important here. And so in an identification sense, if you don't give these agents data, they can never tell who they can trust. There's no way to tell who you can trust. And I think that's, it sort of goes back to like Descartes or something, as like a philosophical point that in order to learn anything about the world, you have to have some axiom that says there's something I believe is real and I trust, whether it's my five senses or the Bible, and if agents don't have that reference point, that they can never tell, maybe all the media is just, a big reality show that's all made up. Maybe it's real. Maybe we landed on the moon. We didn't land on the moon. Who knows? I got to believe in something a priori in order to be able to learn. And so these agents can't get away from the fact that they need these repeated observations to figure that out.
So Matt, if I may, I think we're already a few minutes past, so let's formally end the session here. But there's at least one more question from one of the folks with video interaction. So if you have a couple of minutes, you could stick around and still take questions, but let's formally end the session here.
Great.
And thank you very much.
Thanks so much, everybody.